Good afternoon. Looking at Chapter 1, Section 2 for Calc AB. And we're continuing on with the notion of limits, only today we're really going to look at the formal definition of limits. This will involve two Greek characters, epsilon and delta. These are the lowercase versions of the Greek symbols epsilon and delta. And we're going to get into the formal definition, which is written here, but I also have it a little bit later, so let's just keep moving forward. The idea, the notion here is the limit of a function is the height. We know that, right? The limit of the function is the y value that we would expect to get when we get close to a particular x value. Let's just say this is our x value right now. As I get close to x, coming either from the left or the right, then that has a y value attached to it. When I put in that value, I get out a value. True? That is going to be close to some value L. We understand this portion of limits. As the limit approaches c, that I'm going to get some value L as an output. Here, C, L, delta, and epsilon are all real numbers. And when x gets close to C, say either delta above or below C, then we get a y value that's close to L. No more above it or below it. So here I'm just, what I'm doing is I'm tagging on the same distance epsilon or delta above, delta below. I subtract delta, I add delta, and it gives me this region centered around C. Same's true over here. I pick up an epsilon, I subtract an epsilon distance, and I get this band occurring centered around L. Well, what we want to do with this definition is define what epsilon value could be or what delta value could be. I want you to be able to tell me, well, how close do I have to be to C in order to come out to this limit L? And that's kind of what we're after. So, definition of a limit, let f be a function defined in an open interval containing C, except possibly at C itself, because perhaps C is not in the domain, so it would be a excluded value. But we can get in an interval around it. And let L be a real number. That gives us the statement that we're very familiar with, the limit statement. The limit as x approaches some value c of f of x, then the limit is L. That means for each epsilon greater than 0, there exists a delta greater than 0, such that if, well, I know following an if statement is the hypothesis, right? So here's my hypothesis, that if my x value, chosen some x value, is close to C, matter of fact, it's within delta distance of C, then my conclusion is that my output, my y value, f of x, will be reasonably close to the limit, and matter of fact, it'll be within epsilon distance. Epsilon and delta, we're going to try and put some number values to these, but just in general shape, this is what the definition of limit is. Let me clear off that extra writing. Now, let's visually look at this and see what does it mean. What is it implying? Well, if I stay within delta distance of C, either above or below, I hope you can see this. There is a distance then of equal distance on each side, delta above, delta below. This would be a negative delta because it's going to subtract away. This gives me a right-hand point of C plus delta, gives me a left-hand point of C minus delta. As long as I select some x value that's close to C, then I should expect an output that's close to L. Matter of fact, that distance will be epsilon above, so this would turn out to be the limit plus some epsilon, and this will be the limit minus that same epsilon. So that'd be negative epsilon below, positive epsilon above. Kind of creates this little region, this kind of sweet zone, right? When I put in an input in this region, I can expect my output, my y value height, to be in that same band, that horizontal band. Maybe my function is coming, through something like that. So as long as I'm within C, I can expect my output to be close to L. Well, how close to C, right? How do we know that? I want you to see this computer-generated one. So here's that epsilon and delta going on. If I stay a certain distance close to A, they switched us to A here, then I can expect my output to be close to L. Watch what happens as I change delta. So this little slider is going to change my delta. As delta gets smaller, notice that this darker purple also gets smaller. Epsilon gets tighter and tighter too, doesn't it? It's as we get closer to our A value, or what we call C, if I get really, really tight, well then it's going to narrow this output band that's expected. If I let delta get large, well then I get a broader range of output that could be, expected. Hopefully that's a nice visual for you. Well, let's do a problem because I know this can be confusing. And up in the right in the green, I've got the formal definition of a limit, something that you really will want to kind of memorize. And we'll work this problem. So given the limit, and here's the problem, it says the limit of 2x minus 1 as x approaches 3 is equal to something. Well, I know it's equal to some numeric value, because polynomials behave nicely and we should be able to get a limit value on this. Matter of fact, I can simply plug 3 in to get my limit. I'd have 6 minus 1. This has an L value of 5. I know what my function is because this right here is my function. 3 represents the C value. As I approach C, here's what I can expect for my L value, my limit. The problem says find delta such that the absolute value of the function minus the limit, f of x minus the limit, is less than epsilon. And they gave us a value of epsilon. They want it to be 0.01. So on this, we're kind of working backwards. We're saying we want to guarantee some output in this range. Matter of fact, we're going to let it be 0.01 distance above the output, the expected L value, and 0.01 below the expected L value. Then, whenever x minus 3 is less than delta, this will be true. Remember, this is kind of the hypothesis that we're working with. The question says, what do I have to choose for delta then in order for the output to be within this epsilon? You kind of work these backwards. So we're going to start with this statement. This mathematical statement here says the absolute value of x minus 1 minus 5 is less than 0.01. We can simplify inside the absolute values, so that gives us 2x minus 6 is less than 0.01. Factor a 2 from this, and if I do so, 2 would come out and it would leave me x minus 3. Since 2 is positive, there's really no harm done in bringing it all the way out of the absolute value sign. And I end up with a statement that looks like that. Now, let's just divide by 2. And that gives us the absolute value of x minus 3 is less than 0.005. And I really can't take that any further. It's simplified basically as far as I want to take it right now. But the cool thing is, look over here, what we were trying to find was delta, true? And this looks exactly like that. I got absolute value of x minus 3 is less than some number, and that some number happens to be 0.05. I just found delta. Delta is 0.005. I think I said it wrong before. Yeah, so we're at 5 thousandths of a unit. So as long as I choose something, this is what a linear function, 2x minus 1. So here's my function. As long as I chose, and we're centered at 1, 2, 3, here's my C value of 3. If I stay 0.005 on either side of my C value, then that creates this vertical band, and I can expect my output, when I put in 3, I get out, would we say 5 was the limit? That's our L value. Then I can expect some output to fall in this band, and it will be within 0.01 above and 0.01 below. And here's kind of that sweet zone that we were talking about. Try another problem. Assuming the limit of 6x minus 4 equals something, and we've got x approaching 1. We also know that epsilon is set at 0.001. So we want to be fairly tight to L, don't we? We want to be an L plus epsilon here or an L minus epsilon, and this doesn't give us a whole lot of leeway, a thousandths, right? This is an easy limit to find. Put in 1, I'd have 6. 6 plus 4 is 10, so there's our limit. For these problems, let's start with the conclusion and then work our way back to the hypothesis. So I'm going to take and set it up. I know that it goes f of x minus L. I need my function's output, 6x plus 4, minus my expected limit of 10 to be within a certain distance. And that distance of epsilon was defined for us as 1,000th. I want this to look like, where am I trying to go? My goal that I have in mind is that I'd have the absolute value of x minus c. X minus, this is my c value of 1, and I want to know what that delta should be chosen as. How close to x to, or how close to 1 does x need to be? All right, simplify this side out. Do the work that we can possibly accomplish here. A little bit of algebraic manipulation. It's got a 6 in common. That would leave me 6 times x minus 1, absolute valued 0.001. Factor the 6 out because it's positive, and unaffected then by the absolute value. And divide by 6. I'd have x minus 1 is less than 0.001 divided by 6. And I could let you calculate that. It is approximately 0.0001 repeating 6. There, we've got it as a value. Now, did I end up with a statement that looks like this? Indeed we did. We have down here x, the absolute value of x minus 1 is less than 0.0001 repeating 6. That means then that delta should be selected to be 0.0001 repeating 6. What about a more general case? What delta should be chosen for any given epsilon? Oh, they aren't defining epsilon this time? That's what they've been doing in the past too. And I see, nothing given for delta either. Well, let's just start with the conclusion and work our way backwards. So the absolute value of f of x. F of x is this function 3x minus 2 minus my limit. Oh, forgot to calculate my limit. Throw it in quickly. 2 times 3, 6. 6 minus 2 is 4. So I have a limit of 4. Absolute value is less than some epsilon. But I don't have a value for epsilon. That's okay. We'll let it be a variable. Let's do the manipulation. 3x minus 6 less than absolute value of epsilon. That gives me, let's factor the 3 out. X minus 2 is less than epsilon. Okay. That is kind of the end of the road. Oh, not the end of the road. Let's do one more step. Epsilon divided by 3, how about? How does that match up? Well, I probably should have started with this, shouldn't I? Let's also get this. Our goal that we have in mind is that we want the absolute value of x minus c. What is c? C is the value x is approaching, isn't it? That's 2. So hovering around 2 has to be less than delta. Imagine that. This worked out perfectly for us. So what I just have concluded is that my delta is going to be written in terms of epsilon. What delta should be chosen for any given epsilon? The delta that should be chosen is the delta that equals that. So I want delta to equal epsilon divided by 3. Very good. We'll stop for now.